Let me show you something that's I was just looking. I was writing some code and I was looking at the x86 and the history, and I found a few things that it might just be curious to look at. So this is the x86, the Wikipedia page on the x86 that has all sorts of history since 1978, and the first 8080 and 8088 were created, 16 bits and 32 bits, and then it gets um, to where I was looking 64-bit, in the introduction of the 64-bit CPUs with the Intel. The AMD actually was the first one come up with it in 2003. But it wasn't until the Nihalem, at least that's my experience, that 64-bit were actually used in in the server side. We had actually all the other server computers being all the programs being created. I was part of that. I was charged with changing all the code and adapting all the code into 64-bit. It was about here, the Nihalem and Westmere and the Intel Core, about 2008. I remember that very well. And one of the things that I noticed when that happened was an immense increase in performance, both on the server side, and not only because of by that time we were actually using tons of cores, and we had more development of more code with more threads and so on. But that's what I want to show you is the actual the assembly instructions. They changed, and there was an immense improvement in performance because of that. So the basis of so you can understand how this development took place. You need to look at two documents from Intel. These are my reference documents when I use to develop code. One is the Intel optimization reference manual, 64 and 32-bit. It has tons of information, interesting optimization guidelines that you should look at. One of the things that it's here, it's somewhere in here, is that 32-bit applications, 32-bit instructions are actually faster than 64-bit instructions, which is something that some people don't actually believe, but it is there. I'll try to find later on. I'll post in the comments, or but it's here somewhere. And but why is that 64-bit programs are faster than 32-bit if 32-bit instructions are actually faster than 64-bit instructions themselves? The reason behind this is in the ABI. The 64-bit ABI is much better designed than the 32-bit ABI. The 64-bit ABI is in this document here. You can go to the softwareintel.com and download this PDF. This is the draft version. I think there is a newer version of this, but that's what I have been using for a while. And there's tons of information you should read if you are a developer. If you deal with server-side code and trading, high frequency trading, you should know this document. Both of them actually, the Intel, if you develop for Intel, of course, and the ABI. You have to. They are essential for writing high performance code on in trading or in general. I I want to show you a couple of examples. I'm gonna use the Godbolt, GCC Godbolt. This guy is made this excellent tool, and it's so interesting, so much better than what I have been doing is going into a virtual machine or a server and generating, compile the code by hand on Emacs, and then creating the disassembly of that code. This does everything for you. I like it very much. This online code. It doesn't run the code. For that, I use something called Coliru. Yeah, stacked root. It's very. I don't know why it's doing this, but it's it's a very good. You can actually run this one. You can actually run on Godbot. It just allows you to explore the assembly and how it's created. Let's create a few examples, and I'll show you why the 64-bit ABI is much better in terms of performance than 32-bit. Well, let's just create an example. I had it done before. Let's try to repeat. Let's create this function that just returns square of the value, right? The here you can in this tool you can select the compiler that you're using. Let's go with GCC 6.3, the latest one. Let's just do an optimized build, or just without an optimized build. This is the code, and the right side is the actual assembly code that's generated by the compiler. Because we are not running with optimized, it's just doing a ton of stack manipulation here. I'm not gonna explain what this is doing, but it's basically starting and then loading from the stack. This is just a waste of time. These two instructions right here. What we can do, let's run with optimize, then that's the actual code. This To understand how the parameters are passed, you have to look into the ABI, right? And in the ABI, if you go into, where is the page? Parameter passing, yes, 323. That's the section that defines how the arguments of a function are stored, are passed between two pieces of code that are compiled in a separate sources. And this is actually these three lines here: classification, and that's it. This is the bread and butter of every developer. You should know this section. So there are pointers, there are bool, char, short, int, and long are considered integers, and basically float and double are of the class SSE, right? This is not really important. So these are the three important classifications: pointer, integer, and SSE. If you scroll down, there is also how aggregate are created, are stored, but we go there in a minute. Parameter, okay, passing arguments. Once the parameters are classified, the register get assigned left to right. If the class is memory, everything is passed on stack. If the class is integer or pointer, then it's passed in RDI, then RSI, then RDX, and RCX, and then R8 and R9, right? And by the way, the R8, R9, RDX, RCX, these are all registers in the, you see, RCX, RDX. It's at 32 bits. That's why it's E. But it's an RDI and RCI, RSI here. That's it. These are the registers. If you go to this Wikipedia web page, you can look at this is a comprehensive list of all the x86 registers. Okay, parameter passing. If it's integer, this is what we're looking at. It's RDI, RCI, RDX, RCX. What does it mean? It means that if I pass several several arguments, they are going to be stored in that order. So x, v, x, z. If you do this, z, 3 times z, 5 times x. So v is going to be passed in to 1, 2, and 3. V is going to be passed in RDI. X is going to be passed in RSI. Z is going to be passed in RDX. Let's just pass another one. Y. This is going to be passing RCX. If you do something with these guys, return, what you can see. So the V, which is the first one, is RDI. You see here, this is the EDI because it's 32-bit. If it was in 64, then it would compute as you would have RDI here instead. So this is squaring RDI, then it's loading. This is actually a trick. This is actually RSI plus RSI times 4, which is 5 times RSI x. This is just adding. This is the same thing, RDX plus RDX times 2, which is 3 times z. And this is 4 times the RCX, and starting in EAX and returning. So the return is stored in RAX or RDX. So if you see, RAX is 64-bit or AX is 32-bit. Okay, and it's this prefix R or E is valid for all the others too. But so you understand that now that each parameter is passed on a register. If you change this to 32 bits, everything changes. You see that there's much more assembly code, even in optimized. Let's change back to 64. You see? And the key important thing here is this. It is actually loading from memory. There's lots of memory loading for each of the parameters, because in 32-bit all these parameters are stored in the stack. The parameters for function calls are passed in the stack. They are never passed in as in the registers. Only the return value is passed as in the A register. That's for historical reasons. But that's the biggest advantage of 64 bits. The assembly instruction changes a lot, and in the case of the 64-bit, everything is passed in the CPU. So when one function calls another, there is no messing up with memory anymore. Everything is inside the CPU. It doesn't need to make any external access, even cache or the main memory. It's everything is passed as much as possible inside the CPU itself, which is a performance optimization. It's incredible. It makes a huge difference in time and preservation of the cache integrity as well. That's another point that improves performance. But one interesting thing about this is when you have all the parameters passed on on the CPU on register instead of in memory, you it ends up with some things that are counter to intuitive. Well, see for example, if you pass a parameter that is a struct, let's create a struct that has two integers and a double. I'm doing this because this struct actually is part of the one example that's in the ABI. It's here somewhere down there. Here you go. That's a struct. And what it does is there is a passing, bounds passing. There is a point here that's okay. Here, the classification of aggregates. Aggregates are structs, basically, right? If the aggregate if it qualifies, then this is gonna be applied. Each field of the object is classified recursively, and they are treated as arguments. So what that means is, if you have a function where you pass a parameter, param p, okay, and then let's do something with it. Let's return pa plus pb, okay, and let's compare this with another function where you pass the struct by address a plus pb. Let's look at what happens in the generated assembly. So for F2, PA and PB are passed inside RDI. If you follow the rules there, it's explaining here that these two values are going to be packed in the 64-bit register, because these are two 32-bit integers. They are going to be, these two guys are A is going to be in the lower 32 bits of RDX. B is going to be in the upper 32 bits of RDX. Okay, RDX. And this is going to be passed in XMM0. You can look at the rules, and the rules are going to tell you that for types of SSE, when you go in passing, in the class SSE, the next available vector register is used. The register are taken from order XMM0 to XMM7. That's, and for integers is RDI, RDX, and RCX. So when you pass by value, A and B are passed in RDX, and D is passed in XMM0. So that's what is happening here. It's taking this RDI is the lower 32 bits is A, right? It's shifting 32 bits, shifting right the RX, and then adding them together. And because the return value, you can look at here in the ABI, the return value, if the class is integer pointer, the next available of the sequence RDX is used. So because we are returning just one integer, RAX is used. Then that's it. Then it's adding the RDI with RX, and it's returned in the register itself. But that's all. There is no memory here. Now, when you pass this struct by reference, you are passing a pointer. The function has to access memory, but that's what it's doing here. It's accessing memory and taking the fourth byte, the integer stores in the fourth byte of this pointer, which is B, right? And then adding to the integer in the first pointer. This is equivalent to 0 here. And adding and returning. But there are two memory access when you pass by reference. So if you just from a naive point of view look at these two functions, you would say that this one, that passing by reference, is faster. But when you look at this, and when you look at what the ABI is doing, it's actually more efficient to pass by value because it's just packing the parameters in there in the CPU itself. So that's one big performance consideration you need to have. Sometimes you just have parameters and structs that several values you need to pass. Instead of passing as a list, just pack them and pass like this. It's much more efficient. Um, One last consideration I wanna do is when you rely too much in templates, as in the case when you are you are deep inside meta template programming or in all the modern C++. Unfortunately, what happens, you lose connection between the code that you write and the assembly instruction generated. That's and this kind of things, this kind of optimizations that you could really look if you have plain functions like this. Like when I say plain, it's non-templated functions. You lose connection to that, and this is essential for writing high frequency or any code that it's supposed to be high performance. That's a big point I have spoken, and it's not really well understood by people. Um, it sounds some people say that it sounds petty and revengeful for some reason, but it's not. It's just that that's one method that I like to do. I like to write code and look at the assembly instruction and try to optimize, try to take advantage of what the platform gives to you. Because if you actually change the compiler, or if you change, for example, this is it doesn't change much when you go to the Intel compiler, but if you change to another platform like ARM64, it's a different game. It's the way that the ABI is different. The option optimization is different, and actually the optimizations for ARM are bad for both GCC and CLang and so on. But that's another topic. So I just wanted to show this optimizations you can do in how the 64-bit improved the performance tremendously over the 32-bit ABI.